Okay. Hi everyone. So today we are going to see one of the important article from the partial differential equation. Actually, I'm not saying I should not say it is important. Actually, it is one of the difficult article from the PD because there are only two articles which are difficult in LD that we have. One is this Lagrange's Lagrange's differential equation, and last one is a Charpit's. So these are the two little difficult articles. Otherwise, this topic is a very simple. Okay. So today, let me discuss the theory part of this Lagrange's differential equation. So first of all, we are here in the method of solving the partial differential equation. So we are going to solve only first order partial differential equation. So that is only in our syllabus, first order PDE. So first order PDE means maximum this dou z by dou x and dou z by dou y will appear in our differential equation. So the general format of first order PDE is f of xyz pq is equal to 0. So it is maximum relation between the five things which are xyz and p and q, where z is a function of x and y. Okay, so now as we are going to solve the first order PDE, the solution must contain either two arbitrary constant or one arbitrary function. We already seen that when we eliminate two arbitrary constant or one arbitrary function, we get a first order PDE. So the final answer either we have to write down as a in terms of a two constant like in AB, or it is in terms of one of the arbitrary function. Okay, one of the arbitrary function. We'll see that. So now come to our this first type, which is the Lagrange's differential equation. The form of Lagrange's differential equation is this one: pp plus qq equal to r. Okay, pp plus qq equal to r. So I will write it here again: pp plus qq is equal to r. So this capital PQR are the function of xyz. So remember, whenever you observe, because right now, yes, we are going to see this is the first type. Once we complete this 5 to 6, total 6 types are there. Once we finish it, you have to identify, because in the exam it will not be given solve the following Lagrange's differential equation. The question will be only solved. So the first step is identification. So we should see the equation is in the form of pp plus qq equal to r, where capital PQR are the function of xyz. So to get the solution of Lagrange's differential equation, we use Lagrange's auxiliary equation. This is the Lagrange's auxiliary equation. Dx upon p is equal to dy upon q is equal to dz by r. So we are going to get here one of the auxiliary equation, dx upon okay, so whatever written there. Now in this auxiliary equation, now there is not a unique method. That's the problem actually. There is not a unique way to solve the Lagrange's method. You have to think every time differently, and you have to see how to get two solutions. Once we get a two solution, okay, like u is equal to a and v is equal to b. Okay, u is equal to constant, so and v is equal to constant, then phi of uv equal to 0 is a complete solution. So the final answer always we are writing it in terms of a one arbitrary function. So solution of Lagrange's equation comes in a one arbitrary function. Now right now let me come to the way how we get that u and v. Okay, so that is a different thing. To get u and v, so first always you think, the first step you think direct integration. Is it possible you can integrate it directly? Now when you can integrate directly, suppose this equation dx upon p is equal to dy upon q. Suppose this when we consider only this ratio dx upon p is equal to dy upon q, and if you are able to write it in a variable separable form. Okay, you already know what is a variable separable form. Take a terms of x on one side with a dx, and take a terms of y on the other side with a dy. If you are able to do that, you can integrate it, because a function of x into dx is equal to function of y into dy, and the integration is possible. Then you get one of the solution. For example, suppose there is a dx upon x is equal to dy upon y. So integration is a log x is equal to log y plus log c, and that you get the one of the equation there. So that is considered as a direct integration. So That about our first thing, that is a direct integration. Here, this is the first thing that we've seen, which gives you a variable separable form and you can integrate it. So that about the first method you should think on the problem first. So observation is required. Okay, you require observation. You should see whether it can be written in a variable separable form. Next, you have the next thing that we have is a multiplier. So this is the second thing, using multiplier. This is again important. A multiplier comes plays a very important role again. Now, what is the multiplier? Now, multiplier can be the variables x, y, z. The multiplier means it can be variables. I written x, y, z. It can be x square, y square, z square. It can be 1 by x, 1 by y, 1 by z. Okay, generally they are like this only. Okay, so multipliers are a function of x. Indirectly, I will say function of x, function of y, and function of z. Or it can be a constant like a, b, c, lmn. Okay, uh, once we'll see the example, it becomes more clear. So suppose one of the PDE contains the constants uh, like a, b, c. A is a coefficient of dx, b is a coefficient of dy, and c is a coefficient of dz. You can try that abc as a multiplier, or sometimes that lmn, l, m, and n are appeared in the differential equation. You can try that also as a multiplier. Okay, so now what are that multipliers? But yes, we can multiply by any non-zero thing to the ratios. We know still the ratios remain same. But here our aim is to select the multiplier. Our aim is to select this multiplier so that this sum of this PQR sorry, when you multiply by that multipliers to that PQR, their addition should come as a 0. For example, suppose my multipliers are, let I say multipliers are xyz, my multipliers. So there should be that xp plus yq plus zr should be 0. What I'm saying, that when you select the selection of multiplier should be such that the sum of a denominator after multiplication should be 0. That's the important thing. Now, theorem of equal ratio says whenever you select the multiplier so that the sum of denominator is a 0, sum of numerator should be 0. Okay, this is the important. Sum of numerator should be 0. So that will gives you directly x dx plus y dy plus z dz should be 0. Okay, what happened? We have selected that xyz multiplier so that sum of the denominator is a 0. In such a case, I assume that xyz are multiplier. Multiplier can be a different, that you have to find it by hit and trial, by observation. Okay, so once I assume in this example, suppose that xp plus yq plus zr is a 0, then automatically that sum of a numerator is a 0, x dx plus y dy plus z dz is a 0. Now integration gives us the answer. If you integrate this equation, integration of x dx is x square by 2, integration of y dy is y square by 2, this is a z square by 2 is equal to c, and we get a solution. That's the end of the one of the solution. Okay, so this way the multiplier plays the role. Okay, we'll come in more detail in the examples. You will come to know. So we are just finished the two things, two ways of getting a solution. First is a direct integration. This is the first is a direct integration. Second is a multipliers. Okay, and the third thing is a theorem of equal ratios. Now the last thing that you are observing here, the theorem of equal ratios. You can use a theorem of equal ratios to get the solution. We know if this ratio that we have started here, dx upon p is equal to dy upon q is equal to dz upon r. So you are free to apply componendo, you are free to apply dividendo, both component. You can do anything, but try to get, for example, if I write here dx minus dy upon p minus q is equal to dz upon r. Now, in this case, this denominator should come in terms of like x minus y. If a denominator comes x minus y, it's a derivative present in the numerator. And we know f dash x upon f of y, the integration is a log f y. Oh, sorry, f dash x upon fx, the integration is log fx. So if the derivative of denominator present in the numerator, this integration you can say log of x minus y. So you have to think that way. if you take like dx minus dy, if you take dx plus dy, if you take dx minus p is equal to dy minus q. Okay, the first example of Lagrange's differential equation. So if you observe the differential equation that we have is in the form, this one is pp plus qq equal to r. Okay, this is a capital, so this is the capital P, capital Q, and this is the capital R. So if you compare with this capital PP plus capital QQ is equal to R, that form, we get that PQR values. So the solution always started with the Lagrange's auxiliary equation because it is a Lagrange's form. The Lagrange's auxiliary equation is a dx upon p is equal to dy upon q is equal to dz by r. Only the values of PQ are replaced. So up to here, everything is a simple. Now our method starts. So three methods I told you. The first method is obviously the direct integration. See the variable separable form and integrate it. Next method is a multiplier, and the third method that we have is a theorem of equal ratios. Now remember, Lagrange's equation have more than two solutions also, so you have to take any two of that and then combine with the arbitrary function and you write that as answer. Okay, so right now the first thing you can observe here is dx upon x square is equal to dy upon y square is in the variable separable form. That can be written in the variable separable form. So considering the first two ratios, integration of 1 upon x square dx is a minus 1 by x, integration of 1 upon y square is a minus 1 by y plus c1. So we get 1 by y minus 1 by x is equal to c1. So you get like u is equal to c1. That is one solution. U is equal to constant. You got one solutions here. This is only for your understanding. I written here. No need to write this part. This is the first answer you are written. That is u is equal to c1. Now, to get the second solution, again come to the equation 1, this equation 1, and again try to observe what you can do it. Okay, the simple thing that you observe, if you take this dx minus dy, if you take dx minus dy, denominator comes x square minus y square. Okay, this x square minus y square, which have the factor x minus y into x plus y, and if you equate with the last ratio, this x plus y gets cancelled, and you got again a variable separable, means you can integrate. You can observe the derivative of a denominator like x minus y derivative is a dx minus dy present in the numerator. So integration of this LHS is a log of x minus y because it is in the form of f dash x upon fx. F dash x upon fx is a log fx. So it is in the same way. This is a derivative of denominator z. Derivative of z is a dz present in numerator, so log z. So both are in log. So I'm taking constant of integration also in log. So log a minus log b is a log of a upon b, and taking anti-log on both sides, you get x minus y upon z is equal to c2. So you get another solution v equal to c2. So at the end, don't forget to combine this solution. The pi of uv equal to 0 is known as a complete solution of the first order PDE. So final answer, you will get it as a pi of 1 by y minus 1 by x comma x minus y upon z. This is the comma. Okay, so this function of u comma v, function of u comma v is equal to 0. So we get answer in terms of one arbitrary function. So that is the final answer. Okay, so that about this first example. So welcome in the second example of the Lagrange's equation. So again, you can observe only P and Q are appear. So it is in the form of PP plus QQ is equal to R. So that is in the Lagrange's form. So PP plus QQ equal to R. This is our Lagrange's equation. In the Lagrange's equation, just to replace that capital PQR by comparing. So this capital PQR we replace in the denominator. Okay. So we got dx upon P is equal to dy upon Q is equal to dz upon R. And now we have to find two solutions. So see the way you can observe the denominator. If you observe the denominator, this y minus z plus z minus x plus x minus y, this sum is coming 0. Okay, so just if you select 1 by x square, 1 by y square plus 1 by z square as a multiplier, that means we are going to multiply this by multipliers to the numerator as well as in the denominator. So in that case, the sum of denominator is coming 0. So the sum of numerator, this is the important thing, that is sum of numerator should be 0 because they are multipliers. So the word multiplier itself indicates, that sum of a denominator is a 0. So that indicated the sum of a numerator is a 0, that is dx upon x square plus dy upon y square plus dz by z square should be 0. Then only that denominator can be 0. That is the theorem of equal ratio says. So once you get that, integrating now, integration of dx upon x square is a minus 1 by x. This dy upon y square is a minus 1 by y. Dz upon z square is minus 1 by z is equal to constant. So that minus sign I will shift it to the RHS, and that c is replaced by c1. So this is u equal to c1. One solution we got. Now, right now, I can observe this instead of one of the x, if we take in the bracket, it become xy minus xz. Here is a, sorry, I will write some again, just a minute. If we take this one of the x, will keep here as it is, and if you take another x in the bracket, xy minus xz, is y, yz minus x y, this is a z, and that is a xz minus yz. You will observe right now also the sum of these three brackets are coming 0. This xy gets cancelled with this minus xz cancel with this plus xz, this yz will get cancelled minus yz. So sum of denominator is again coming 0 provided this x, y and z are not there. So we'll take 1 by x, 1 by y, 1 by z. We'll take this 1 by x, 1 by y, 1 by z are multipliers. So this is the second way we selected the multipliers, so that the sum of a denominator is a 0. So sum of a numerator should be 0, because we are multiplying 1 by x, 1 by y, 1 by z to both denominator and numerator, and we are adding that. Okay, so addition of multiplying the multipliers, that is a 0. That addition of the multipliers, first we are multiplying and then adding, that addition is a 0. So because of that, the numerator should be 0. And now integration, 1 upon x integration is a log x, 1 by y integration log y, 1 by z is a log z, and that is log c2. Everything is in log, so we taken constant again in the log, and we got xyz equal to c2 as a solution. And at the end we written phi of u comma v is equal to 0 as a complete solution. So this answer comes in one arbitrary function. Okay, that about a second example. There are two more examples you can identify on the page LD handout, and you can try to solve that. Okay.